Okay, so here we are. I think I finally figured out how to do this. This is like take 50 of all this, and I'm not going to quit until I get it right. Okay, so here we are. It's the beginning of the end. Only 6 more weeks to go, and the way it's going, it just might be the end with all this corona stuff. But hopefully not. Hopefully everybody's taking care of themselves and doing what you need to do. And I know it's tough. It's tough teaching it this way, and I imagine even harder learning. I never liked learning online, and I don't really like teaching online. But that's what I gotta do. And I think I got something figured out for you guys. Taking me some little time to get this under going, but I'd rather much be in the classroom with you, teaching you face to face, especially your group. It's a really good group, and you guys always make class fun, and that's what's great about teaching. Just have every once in a while have a class like yours guys. So anyways, I hope we can get this done. I can get you what you need to do to move on and with your world of chemistry, because I don't know if you'll be using it in the future or not, but you could if you pay attention to the world around you. You'll see that it does apply in so many different things. I gave a PowerPoint announcement about your equilibrium worksheet that I gave you before break. I would like you to get that done. So answer all the questions I circled ahead you guys do, and get that to me by, I guess, Sunday next. By this coming Sunday, that'd be great. Just make sure you can send it to me as picture file, scan it, or you can doc file. Either anyway, in the subject line, say Chem 122 equilibrium, because I need to sort all this stuff out. Okay, so we're moving on. We are going to continue with equilibrium and apply equilibrium to different things. And the first place we're going to apply it to is acid base. So we talked about acid bases in 121 a little bit, and then we talked about acid base neutralization reactions. Also talked a little bit about how acids, what makes an acid an acid. So if you remember, if you look back in your notes, if you still have them, you'll see that acids were covalent compounds. But one of the things that are kind of odd about them is that when you put them in water, is they behave like ionic compounds. They split apart. And they split apart into positive and negative ion, just like ionic compound. So, and the positive part is always an H+. And that's distinctively what makes an acid. Acid is the H+ that is given off. And we'll see that in the as we go through these. Also, this concept of acids and bases has been around for a very long time. Chemistry itself has only been a discipline for about 250 years or less. But people that have been doing chemical reactions, even though they didn't call them that, have always kind of realized that there's things that behave one way and other things behave the other way, and they could kind of sort them into those two categories. And I think, I'm not really 100% sure, but one category they called acids, and another category they called base, but they didn't really know why. And for instance, the word oxygen, oxy means acid, gen means produce. So they came up with the name oxygen way before they knew what it was. So, but they knew that it did whatever they thought an acid does. And one of the things that they sort of noticed about acids, they kind of ate things up. They disintegrated things or whatever. So I guess that's kind of where they put acids. He said anything that sort of chews things up, eat things up, destroys things is kind of acid behavior. And then you have your bases that are the things that get eaten up. Now, as we've learned more and more about chemistry and what really seems to make it work is that we've realized what acids bases are. So what we're going to do is we're going to talk about the elementary way of thinking about acids and bases, and then what we're going to do is expand on that. And actually you'll see how it relates to just about everything we do in chemistry. Okay. All right, so the first formalized definition of an acid is Arrhenius, acid and base. So Arrhenius was a fella in the 1800s, and we saw his name before when we talked about energy of activation. There was a formula that related to that he came up with to help us figure out the energy of activation of a reaction. But he also came up with the first formalized version of an acid base, and it's very specific. An acid, he said, and this is paraphrasing a little bit, produces a H plus in water. So we have to be a little bit careful what H plus means. So H plus means hydrogen that's lost an electron. So hydrogen has a proton and an electron. So when you put it in an acid in water, what happens is the proton comes off the water, leaving the electron behind. So it produces an H plus. So you're gonna see that the word H plus is going to be interchangeable with the word proton. But we have to be careful when we talk about proton, because protons in this case have to come from hydrogens. Because if we say an acid is something that gives off a proton, it's not true, because if carbon somehow gave off a proton, it wouldn't be carbon anymore. So the only thing that can give off or produce protons is an acid, a hydrogen, and water. Okay, so then we have a base, and this really is specific to Arrhenius. Okay, he said that bases are hydroxides, OH minus, and when they're in water, so metal hydroxide. And actually, when you put these two guys together, acid and base, what you do is you form water, which you see in this reaction here. So we talked about this reaction 121. Took an acid base and combines water and formed ionic compound, otherwise known as a salt. And so considering this in reaction, say we took hydrochloric acid, aqueous, sodium hydroxide, aqueous, and put it in water. And you do this reaction, all takes place in water, and it also produces water and sodium chloride. The ionic equation is the HCl splits apart, the H plus the Cl minus, so this is the acid part, and so the Na and Cl cancel out, so they're spectators, and the H plus combines with the OH to form water. Okay, so Arrhenius are very specific, especially the base. Always got to be hydroxide. Okay, Bronsted-Lowry is the next definition, and it's more broad definition. It'll include the Arrhenius definition as well. The acid is basically the same definition. It proton donor. It gives off a proton. Gives off a H plus, and again, it has to be in water. But what's different about Bronsted-Lowry is that the base is a proton acceptor. So hydroxide, OH minus, we saw from the previous reaction, will combine with H plus, so it accepts H plus to form water. But there's other substances that can accept protons as well. It's not just hydroxides. For instance, this example here. So you take hydrochloric acid plus water you will form hydronium ion and a chloride ion. So HCl is the acid because it gives off an H, donates a H plus proton, and the base, water is the base because it accepts the proton H plus. All right. Now just overview of Arrhenius compared to Bronsted is Arrhenius definition is a special case of Bronsted-Lowry. So all Arrhenius equations, acid bases, are essentially Bronsted-Lowry, not the other way around. So Arrhenius are a subset of Bronsted-Lowry. We're going to see in the third PowerPoint of this section, there's three to deal with, three PowerPoints I'm going to have here, that there's even a broader definition called Lewis acid base that really kind of ties everything together. Okay, so let's take a look at another example and look at formic acid. Formic acid is a Bronsted-Lowry acid. I forgot to put Lowry here. Okay, it's kind of important to poor Mr. Lowry. So formic acid is an acid, and it's a weak acid, which is going to be discussed quite in depth in a few minutes. And the weak part has to do with this double arrow here, which will be explained. So the double arrow means that the equation is at equilibrium. It can go both in the forward direction and a reverse direction. Okay. So we have formic acid, right? This guy right here. And it's combined with water. And so what's going to happen is the formic acid is going to have the H plus pop off, donated, and it's going to be given to the water. So this is the acid because it donates. And this is the base, right? And then you form these two guys. Okay. Now, the reaction can go back in a reverse direction. So the formic acid turns into formate. Remember in 121, I said that if you have ic acid and it loses its H, it becomes an 8. So formic acid becomes formate. So formic acid becomes formate, loses its H, and H goes to the water, form the acid. Now, the reaction can go back into the other direction, so both of these also can be acids and base, but it turns out they're the opposite. Now, this guy here, who was essentially the acid over here, is now the base. And what it can do is it can grab a hold of the hydrogen of this guy, and it can form water and formic acid. Now, so the thing to notice is the acid turns into a base when it's at equilibrium. That's because both of these are weaks, weak acid and weak base. And the base can turn into an acid. So we say that the acid, this is a conjugate pair, acid-base pair. Okay. So if there's a double arrow, that means the product side will always have conjugates. So the acid will turn into a conjugate base, and the base will turn into a conjugate acid. All right, so let's take a look at these two reactions here. We've already looked at them, and we can see that what kind of different between them is the arrows. This has a single and this has a double. The reason why this has an arrow only going to the right is because it's essentially irreversible. That means the reaction only goes to the right. And the reason for that is this acid right here is a strong acid. And we'll define what a strong acid is in the next PowerPoint. Okay, this double arrow here tells us that the acid and the base are both weak. Okay, in the top reaction, either if you have a single arrow, one or both of these, the acid or base will be strong. In this case, this is a strong acid, weak base, but they could be a strong acid, strong base, or weak acid and strong base. Okay, strong always pushes it completely one direction. But if you have two weak acid and base, the reaction can move back and forth. So that if you see a double arrow, that means you have a weak acid and a weak base, and therefore a conjugate acid and a conjugate base. If you have a single arrow, there's no conjugate acid and conjugate base. All right, so let's take a look at this example. Hydrogen carbonate with hydroxide undergoes acid-base reaction. So if we look at the HCO3, if you notice, it goes from HCO3 minus to CO3 2 minus. And so the H has come off and been donated to the OH to form water. So this is the H. It's given the H off. And this is the base. It's accepted the H. Because of the double arrow, that means they're both weak and acid and base. And they have to be acids and bases over here. The acid will turn into the conjugate base, and the base will turn into the conjugate acid. All right, on the bottom over here, we can see we have the same guy, but this time it actually behaves like it says it's a base. It's kind of interesting. We'll talk about that in a second. And the reason why it does that is because it's who it's combined with. If it's added to something that's a stronger base than it is, then it can be an acid and vice versa. So this guy, when it's added to H3O plus, will actually accept an H and form carbonic acid and water. So this case, this guy grabs an extra H, forms this. So this is the base, turns into the acid, and the base turns into, the acid turns into the conjugate base. All right, so if you have a substance that's both can be acid and base, and essentially every weak acid and weak base can almost be identified as that, then we call it amphoteric. All right, and the last thing before we for this PowerPoint, hopefully, finally, can't believe it's taken me long to get these 9 simple guys, is to analyze this. So this is an acid-base reaction. What you need to do is tell me which one of these is the acid and base. Since it has a double arrow, both of these are weak acids and weak bases, and therefore these are conjugates. Okay, so there is a mistake here. This should be a 2 right next to this guy right here. And maybe I can fix that in a second. So the CH3,2NH will turn into CH3,2NH2 plus. So it's gained H, so it must be the base. This guy is H2SO4, and it loses an H, so it becomes, so it's the acid. So this guy is the base here, conjugate acid. Acid, conjugate base. Okay, hopefully that worked out, and we'll I'll fix this up and put a 2 here and see if that works, and go to the next PowerPoint.